All right, picking up section 13.7, just to wrap up chapter 13. So I want you to think back to Physics 1 and think about system versus surroundings. So surroundings act on something. Are forces that act on something. So the force acts on the Jedi Knight, and normally that something is the system. So is it bringing the force or is it being forced on? So, and this, as you've already seen, really comes back in Physics 2, where we've had to be very clear about, is this a charge that's contributing to the electric field, or is this a charge that the electric field is being forced on? So make sure you read your problems carefully. And draw pictures. It's very important to draw pictures. So for example, if we had a field, minus Q, Q plus, another Q over here, minus Q there, the Q right here, then we'd have to say, what are we observing from? So are we observing from this particular charge? In that case, all of these charges would be contributing to the field, and we would be looking at the force on that charge, perhaps. Are we observing at some random place in space? So maybe we're observing from over here, and in which case all of these charges would be contributing to the electric field. So make sure that you're asking yourself the question, is this a charge that's being forced on, and in which case it's the system, and we need the electric field from the surroundings, or is this a charge that's a part of the surroundings, that's bringing the force and needs to be a part of our calculation of the electric field? And this does get easier with practice, but it is, when in doubt, talk yourself through a problem. Okay, so moving on, 13.8. Is the electric field real? I mean, you've certainly seen the impacts of electric fields, so just think static electricity. So there are two main concepts from chapter 13. And these are concepts that are going to really form the basis of the rest of Physics 2. So if you know E at a location, then you know F equals QE at that location for any Q. So if you calculate the field, then it's just a matter of insert desired charge here, get force out. And what we're starting to see is we can use the electric field to better describe electric properties of matter. And we can do this even if we don't know how the field was produced. And just a fun tidbit, we will learn that if the electric field in air is greater than 3 times 10 to the 6 newtons per coulomb, air becomes a conductor. So there are some real life consequences of electric fields. Okay, so electric fields have an interesting relationship to c, where c is the speed of light. In a vacuum, if we're going to be very precise, where c is equal to 3 times 10 to the 8 meters per second. And also, there's a really interesting consequence of that, is it travels 1 foot per nanosecond. Now, electric fields move at c. So if you produce an electric field, it will travel at the speed of light. So there are some real world consequences for knowing that, for example, an electric field travels 1 foot per nanosecond. Electric fields are how we move electricity through our walls. So if you want to know how long it takes for a signal to reach a wire, 1 foot per nanosecond. And if you're making very precise measurements, that makes a difference. Take it from me. I have made some very precise measurements. All right, so a few other things. These are just conceptual things to keep in mind that we will bring back later on. So let's say we had a dipole consisting of a positron and an electron. So we have electron, positron. So we've got a dipole. We observe the field here from this. Now, electrons and positrons are antimatter, or electrons and positrons are matter-antimatter pairs. And matter annihilates antimatter and vice versa. So let's say, we're detecting this field from, it'd be in that direction. Okay, from the dipole. Now let's say these annihilate each other. So annihilation, Jiminy crickets. They annihilate, they produce 2 photons in the process. And when this happens, at that very moment in time, we are still observing a field. Why? Because it needs to travel to us. So, and we will detect E for a time being equal to R divided by C, where R is the distance it would take to travel from the source of the dipole to where we were making the observation. And so essentially what we have just done here is that if you have electron-positron annihilation, you get 2 gamma particles. And this is actually something that happens all the time. So one of the sodium-22 decays is a result of electron-positron annihilation, and you'll get 2 511 back-to-back gamma rays. Okay, so just like in Physics 1, whenever you are dealing with things moving, there are relativistic corrections. F is equal to 1 over 4 pi epsilon naught, Q1, Q2 over R squared, and E is equal to 1 over 4 pi epsilon naught, Q over R squared times R hat if Q is moving close to C. So, and if Q is moving in X, then 1 over 1 minus V squared over C squared will show up, in Y and Z. So here is just a little taste of what is to come, and this comes right at the very end of Physics 2. All right, this wraps up Chapter 13.